Hi there, class. I wanted to make a video today to talk a little bit about item analysis. This is really the traditional classical test theory item analysis. This is basically just a procedure that we use to kind of quantify characteristics about test items. It helps us identify items that are too easy or too difficult. It helps us understand ways in which we can differentiate between people who scored high on the construct and then low, or high and low performers on the test. There are some good readings, I think, this week that really sum up what's going on, and I'd probably recommend to look at them sort of in this order here. I'd start with the basic concepts and item and test analysis. The Meyer item analysis chapter is wonderful. There's a PowerPoint on here, an item analysis from Wise, which is pretty good. And the others are good supporting documents. Like Wu is a nice formal treatment of classical test theory. So that's kind of how I'd recommend looking through there. I made this little note sheet on here that I'm going through, so we kind of have something to look at while I'm talking to you, and then I'm going to walk you through an item analysis. So, some of the main things about some main item analysis statistics. The main thing is it's really a lot of new terminology. The statistics behind these are really easy. Like the item difficulty is just the mean of the item. If it scored 0, 1, it's the proportion of students who got the item correct. That's the item difficulty. So it's basically just a mean. The higher the difficulty, the easier the question. So it's kind of backwards. So if you have item difficulty of 0.8, it means that 80% of people got the item correct. So lower difficulty actually means lower difficulty score actually means the item is more difficult. These things are really awkwardly known as, you'll see on here that they're known as, they call it p-value. And the P in this case stands for proportion, not to confuse it with a p-value from hypothesis testing. But I'll usually just call it like the difficulty parameter. So, the difficulty is a characteristic of both the item and the test takers. Yeah, I forgot where I lost my train of thought with that. So these are really sample dependent. That's where I was going with this. They're sample dependent. So, the difficulty for the item isn't, really generalizable across different test takers. In theory, if we could keep sampling from the population of test takers, computing then the item difficulty, do it over and over again, then that expected value should equal the population item difficulty. But this is really a sample characteristic. So if you have an item with a difficulty of 0, 1, it really doesn't contribute much to the, it means everybody either got the question right or everybody either got the question wrong. We're really looking for items with difficulties around a 0.5. So around the 0.3 to 0.7 range is typically what we're looking for. They typically say the ideal difficulty is a value that's slightly more than halfway between chance. So let's say we had a 5-choice multiple choice response. So it's A, B, C, D, and E. Right? If you were just guessing across all the items, then you have a 20% chance of getting the item right, with 5 options. So the ideal difficulty for an item with 5 options would be halfway, slightly more than halfway between. So halfway between that is 0.6. So that's why we usually say the optimal difficulty goes around 0.5, because even if you're just guessing, if it's a 4-point scale or a four item response, you'd have a 25% chance of just guessing the right answer. So taking that into account and increase, we were looking for items with slightly more higher difficulty. Next item statistic we're going to talk about is item discrimination. So, if an item measures the construct we're interested in well, then we would expect those to answer, those who we expect those who do well on the test to answer the item correctly, and those who do poor on the test to answer the item wrong. So if our item, it truly does measure whatever the construct is, then those who perform high on the test should get it right. Those who perform low on the construct should get it wrong. So the item discrimination really much refers to an item's ability to differentiate between those who do well and those who do poorly on the test. There's a couple ways we can measure this. There's like the discrimination index or a discrimination coefficient. So the index is basically we split the sample into high and low performers. We can either do this by like taking the upper quartile, or some of the readings talk about taking the upper 27% and the lower 27%, but it's still sort of the same idea. And then we basically just compare those who got the answer correct, the number of those in the high group that got it correct from the number of those in the low group who got it correct. We can also measure this with basically a correlation. All right, so this would be like would either be the point biserial correlation or just a biserial correlation. This is basically a correlation between a dichotomous variable and a continuous variable, right? So this is the correlation between whether or not you got the answer right or wrong, and then the total score. We generally want an item to have a high discrimination. Right, so we're looking for high values on here. Since we can think about measuring it with a correlation coefficient, it ranges from -1 to 1. A low discrimination or a negative discrimination is actually a bad thing. It's saying that those who scored poorly on the test tended to get this answer correctly, tended to get this item correctly more often, which probably indicates something's going on with that item. So, typically discrimination indexes, we're looking, between 3 and 7, greater than 4, they'll say is very good. In the 3 range is good, and in the 0.2 to 0.29 is kind of marginal. Anything less than that really needs revision. Then their negative items are really saying, hey, something weird's going on here. We'll also talk about a distractor analysis, and this is really where we are going to analyze, the incorrect alternatives. So we want to see, it's really useful for discovering whether some of the decoy items, I guess you could say, on the test, how well do they perform? Is nobody selecting option A? Maybe we want to revise it and see, are high performers selecting a decoy item? That's another indication that, hey, something could be wrong with that item. Typically what we do in this is we can calculate a discrimination index for each one of those response options. And we would preferably want that discrimination to be low or even negative for the distractor items. Some of these statistics, like some of the discrimination statistics and stuff, we can get from just a regular reliability analysis. Typically with a set of binary items, whether you got the question right or wrong or not, it's really called the Cooter-Richardson 20 statistic, but it's basically Cronbach's alpha. It's just a generalization of Cronbach's alpha. So you can basically just run your regular internal consistency alpha reliability the same way you normally do, and you interpret it pretty much in the same manner. And then kind of the last point to really hit on is, the item analysis process is really it's an iterative process, right? After we decide what items we want to keep, which items we want to remove, we'd run the item analysis again we'd also run it again. And then you'd want to run it till we have our final set of items.